Let's take a look at problem 15.1. In this problem here, we have a 20-tooth pinion with a diametral pitch of 8, and it rotates at 2,000 RPM. This drives a gear at 1,000 RPM. What they want us to find is the number of teeth in the gear, the theoretical center distance, and the circular pitch. So we know that we have this top pinion right here. We have the pitch, capital P, is equal to 8. We have over here the number of teeth is equal to 20. It has some diameter, d sub P, rotates 2,000 RPM. Then we have this theoretical center distance here where it comes down to our gear, which has some diameter, d sub G. And we know that this rotates at 1,000 RPM, and we're looking for the number of teeth. So that's the first thing we're looking for is the number of teeth. Then we're looking for C, and then we're looking for what our circular pitch, lowercase p, is down here. Now that we've had a chance to look through the problem statement and our schematic, the next thing we want to do is break this down, figure out what information is given to us, our variable names, values, units, how it relates to our diagram, what they're asking us to solve for, and what assumptions we're going to make. So we take a look first here. I redraw my diagram. I have my pinion up top here. I've labeled it there. It has some diameter, d sub P. I have my gear on the bottom here. I've labeled it d sub G. You can see my direction of rotations. Up top for the pinion, I have my n sub P and P. At the bottom for the gear, I have my n sub G here. We know this is 1,000 RPM for the gear, 2,000 RPM for the top pinion, and our theoretical distance between the centers of these two is the value C. Now what I've done here is I've kind of separated these out between the pinion and the gear as far as my given variables go. So if we look at the top of the pinion, N sub P is 20, which is my number of teeth in the pinion. P is the pitch of the pinion. Then we have our speed of 2,000 RPM. We have diameter here of d sub P. Then we move down to our gear, and we have the number of teeth in the gear is n sub G, and that's what we're looking to solve for. Our capital P for the pitch of the gears, we're also looking to solve for there. We know the speed of the gear is 1,000 RPM, and we know the diameter is this d sub G. Now, we don't have numeric values for d sub P and d sub G yet, but that's something that we can solve for both of those. Now, there's three different things they ask us to solve for in this problem. They want us to solve for the number of teeth on the gear, my n sub G, my theoretical center distance, C, and my circular pitch, lowercase p. So again, pay attention between upper and lowercase c. Make sure we understand which one we're solving for and which one we're given within the problem. Assumptions that we need to make before we start our solution to this problem. 1, we want to assume that the gears are spur gears. 2, we assume that the gears have teeth of standard profile. 3, we assume that the gears mesh their pitch circles. So with all those assumptions, there's some key governing equations that we can start off with as we begin our solution. So as we start our solution, what we want to do is break it down into 3 separate parts they'd asked us to solve for in the problem statement. So here we're going to start off with part 1. So what do we know? We know that the pinion has a speed given to us as 2,000 RPM, and the gear has a speed that they give us of 1,000 RPM. So if we know the two speeds of those, what we can do is find this ratio. So we have the speed of the pinion over the speed of the gear is 2,000 RPM over 1,000 RPM, which gives us a 2-to-1 ratio. So with that information, knowing that we have this 2-to-1 ratio here, we know that a 2-to-1 speed ratio is going to require a 1-to-2 ratio in the number of teeth. So we come over here, use our variable names for the number of teeth. Again, pinion in the top, gear on the bottom. So this is going to be a 1-to-2 ratio for our number of teeth, where we know the number of teeth of a pinion is 20. So we can plug that in for our n sub P here. And we get that 20 over some value of n sub G that we can solve for is equal to 1/2. So there's only one unknown in this relationship now, our n sub G. We can cross multiply here. 20 times 2 is equal to n sub G times 1. So n sub G is equal to 2 times 20. Or n sub G is equal to 20, so therefore this is the number of teeth on our gear, 40. So now that we've gone through and calculated the first part of the problem, we can go through and look for part 2 now. So part 2 in the problem asks us to find this theoretical distance C, where this distance C is the distance between the diameter of the pinion and the gear. So in order to know that relationship, what we're going to need to do is solve for the diameters of both the pinion and the gear in order to find this distance between their centers. So where we can go to look for our diameter is to equation 15.3 in our textbook. So this gives us that P is equal to, and this is capital P, is equal to N over D, where P is the pitch, N is the number of teeth, and D is the pitch diameter right there. So D is what we're looking for. So in order to solve for this, we can rearrange equation 15.3. So D is equal to N over P, the number of teeth divided by our pitch that's given to us. Then we want to do this for both the gear and the pinion. So we've solved for N sub G in part 1 of the problem, and N sub P was given to us in the problem statement. So now we see that D sub G is equal to N sub G over our P. And I'm calling this P sub G and P sub P just so we can prove to ourselves later that these are both equal. Now this is equal to, now if we plug in our known value, N sub G we solved to be 40. P was given to us as 8, so 40 divided by 8 gives us a diameter of the gear of 5 inches. Now we can do the same thing for the pinion, and D sub P is equal to N sub P over P sub P, where P sub P is just P, capital P, giving us a problem statement of 8. So N sub P was given us as 20. 20 divided by 8 is 2.5 inches, which is the diameter of our pinions. Now we have the diameter of the gear and the diameter of the pinion. And again, we can look at our gear ratios here. So 2 times the pinion is equal to D sub G. Plug in our values there, and we can back out our P sub G of 8. So we did prove to ourselves that a P sub G here is the same as our capital P for our gear and our pinion there. So that's just a double check if we wanted to prove it to ourselves, make sure we're using the right values. But we were able to get the final answers we needed from our equation 15.3. So now we have the diameter of the gear and the diameter of our pinion. So now that we've solved for both the diameters, the diameter of the pinion and the diameter of the gear, we can continue on with part 2 of our solution. We're now, again, recall we're looking for this theoretical distance C, which is the different distance between the center of the pinion and the center of our gear here. But now we know our diameter, so that means we also know our radius. So here's our radius there for our pinion, and then we have our radius here for our gear there. So this would be radius sub P, radius sub G there. So if we want to find our radius there, we can take half of our diameter. So C is equal to half the diameter of the pinion plus half the diameter of the gear. Put those in. C is equal to 2.5 over 2 plus 5 over 2. Or for the radiuses here, C is equal to 1.75 plus 2.5, which gives us a theoretical distance of C equal to 3.75 inches. So there's our C value there for our theoretical distance between those two. So now that we found our solution to part 2, where they'd asked us to solve for our theoretical distance C, the next thing that we can do is we can go to part 3. In part 3, they're asking us to solve for the circular pitch, or lowercase p. There's a couple different equations we can use to arrive at the solution for this. We're, for this first part, going to go to equation 15.5. So equation 15.5 gives us this relationship here. Our lowercase p is multiplied by our uppercase p is equal to pi. So lowercase p times uppercase p is equal to pi, where uppercase p is the pitch they give us in the problem statement. Rearrange this, so our lowercase p is equal to pi over our uppercase p, or we plug in for p given to us in the problem statement of 8. Lowercase p is equal to pi over 8. So our circular pitch is equal to pi over 8. Now we could also double check and go to equation 15.2, where we have our circular pitch, or lowercase p, is equal to pi times d over n, a diameter divided by the number of teeth. So we plug in our known values here. Okay, so our circular pitch P is equal to pi times our diameter here is 5 inches divided by 40 teeth. So P is equal to, again, pi over 8 if we do it this way. So just a double check using both equations 15.2 and 15.5. Let's take a look at problem 15.4. In this problem here, we have an electric motor driving a machine by means of 3 straight tooth spur gears. So we know we're dealing with straight tooth spur gears in this one's here. The gears are going to have teeth of 16, 32, and 24. So we have 16 for our motor gear, 32 for our idler, and 24 for our machine. These gears have a pitch of P is equal to 8, capital P is equal to 8, and an angle Phi is equal to 20. We know that the idler shaft is supported by bearings A and B. Now if we come down to our diagram here, we can see bearings A and B. We have dimensions of these guys here, where bearing A is 1 inch off the surface plate of our idler, and bearing B is 2 inches away from bearing A. Now if we look at this diagram, we can also see that our motor rotates at 1700 RPM, and we know that it has a torque of 100 pound-inches. So with all this information given the problem statement in our diagram, what are they asking us to solve for? Well, they're asking us to solve for 3 different things here, A, B, and C. For A, they tell us for the direction of the motor rotation shown, so we can see which direction it's rotating here. They want us to find the radial load carried by each of these bearings. Part B, they want us to determine the bearing loads for the opposite direction of motor rotation. So if this were to rotate the other direction, then what would the loads be on A and B? And C, they want us to briefly explain why parts A and B are different with the different direction of rotation. So now that we've had a chance to look through the problem statement and given schematic, the next thing we want to do is write down in a clear, neat, organized fashion all of that information. So we want to know, what do they give us in the problem statement? What are the variables? What are the values? What are the units? Simplified version of our schematic. What are they asking us to solve for? And what assumptions are we going to make for our solution to the problem? So the first thing I do is I read through the problem statement and realize they give us 3 spur gears. We have a motor shaft, a machine shaft, and an idler. So with that information, I come down and redraw a simplified 2D version of my schematic here. We have my motor up top, the gear with 16 teeth, machine over here to the right with 24 teeth for that gear, and our idler has 32 teeth. So all this information is now in a nice simple 2D schematic here. Then what I choose to do next is to break this down into variables and given information for each of those 3. So what do we have for our motor? What do we have for the machine? And what do we have for the idler? So we'll start with the motor, calling this N sub MO for the number of teeth of the motor is equal to 16. Our capital P for all of these, a pitch of 8. We have our pressure angle here of 20 degrees for all of them. And for our motor, we have our speed of 1700 RPM. And we have a torque given to us from the motor of 100 pound-inches. Now for the machine, I can jump down. I know N sub MA, number of teeth of a machine, is equal to 24. Pitch is the same, 8. Our pressure angle is the same of 20 degrees. And for our idler, we know that our number of teeth, N sub I for the idler, is 32. Again, pitch is 8. And our angle is still 20 degrees for our pressure angle. So now that we have all that information, our variable names spelled out correctly with the right indices for them, what we want to do now is figure out what they're asking us to solve for. So again, recall in this problem, there's 3 different parts. 3 things they're asking us to solve for. Part A, we want that radial load on the idler shaft bearings, so A and B, for a given direction of the motor shaft rotation. Part B, they want that same radial load on the bearings for the motor shaft in the opposite direction. So if it starts rotating the other direction, what happens? What are our loads? And C, explain why the answers to A and B are different. So next we want to go through and figure out what assumptions we're going to make for the solution to our problem. So we're going to have 4 main assumptions here. Number 1, we're going to assume that the gears mesh along their pitch circles. 2, we're going to assume that all the gear tooth loads are static and are transmitted at the pitch point. 3, we're going to assume that friction losses in the gears and bearings are negligible. And 4, we're going to assume that the shaft bending deflections can also be neglected. So with these assumptions, we can now start our solution, and we're going to break our solution down into parts. So again, there's 3 different parts, A, B, and C, that we're solving for. Let's start with part A, and with part A, let's start with our idler. So with this here, we're going to find our governing equation, which if we go to equation 15.3 in our textbook, we have the equation here that we have our diameter pitch here, capital P, is equal to the number of teeth n divided by our pitch diameter here. So this was given to us in our problem statement. What we want to do is solve for this pitch diameter here, lowercase d, by rearranging equation 15.3. So rearrange this, and our diameter d is equal to n over p, capital P, where we have now our n is for our idler here that we're dealing with for our specific case, n sub I is equal to 32 teeth, and our capital P, our pitch, is equal to 8, again, for all three of our gears now. Plug in our known values here. D sub I, our diameter for our idler, is equal to the number of teeth of 32 divided by our pitch P. So our diameter is equal to 4 inches for our idler. So now that we've solved for the diameter of the idler gear, the next thing is to solve for the diameter of our motor gear. So now we can use the same equation here, but now plug in for our indices of our diameter for the motor is equal to the number of teeth in the motor divided by that same pitch, which again is 8 for everything. Which we show over here, P sub MO is equal to P is equal to 8 for all three gears is going to be 8. So our number of teeth in the motor was given to us as 16. So we can plug in our known values here. So D sub M for our motor, D sub MO for our motor is equal to 16 over 8 for the number of teeth divided by our pitch. So D sub MO is equal to 2 inches. So from this here, we're going to want the radius of our motor gear. So our radius is half our diameter. So the radius for our motor, right here, R sub MO, is equal to 1 inch. Now, we know from the problem statement that our motor has a torque of 100 pound-inches. So we can recall our relationship between force, radius, and torque. We have T is equal to Fr, where R in this case here is the radius of our motor, R sub MO. So we can plug that in here. Torque is equal to force times 1 inch, where our torque was given to us again as this 100 pound-inches. So we plug in 100 pound-inches equal to F times that radius there. So the only unknown is F. We can rearrange and solve for F. So F sub T in this case here is 100 pounds. And how does this look at here? So this is our motor gear and our idler gear here. Here's our F sub T right there. So next I redraw out my schematic simplified form here where I have all these external forces coming in here that I'm interested in. We have my F sub R. Here's the F sub T that we just solved for based on our torque given from the motor specs right there. It was 100 pounds. And we have our F sub R up here. Now if we want to solve for this F sub R here, we can go back to this relationship from our chapter. It's also given in our lecture slides as well, where our F sub R here coming straight down from our motor gear into our idler is equal to this F sub T that we just solved for our tangential force component there of F sub T times the tangent of that given angle of phi here, where phi is given to us as 20 degrees. So we know the F sub T that we just solved for is 100, and our angle of is given to us as 20 degrees, so we can plug this in. F sub R is equal to 100 pounds times the tangent of 20 degrees, or F sub R is equal to now this 36.4. So we have that right here. This is our F sub R right here is equal to 36.4. And then what we can do is we can look over here and say, okay, well this coming in here perpendicular is the same as this one coming in perpendicular over here, 36.4, and this 100 over here, tangential is this 100 pounds there, same as our F sub T. So then we don't know is the forces that are supporting this idler here on the idler shaft. So that'll be the next step that we want to look for, is to come up with a free body diagram based upon that. So let's just take a look at our idler gear here. We know we have this F sub R coming in here of 36.4, our F sub T of 100, 36.4 coming in here perpendicular as well, and 100 down here as well. So we can see now we have this free body diagram, and we have this F here coming up, acting on the shaft for the idler, and what we need to do is solve for this F. So now what we can do is zoom in and draw out the free body diagram for idler a little bit larger so we can clearly see what's going on. Again, we have our idler here, we have the center shaft here with some support load F, which is going to have components F of X and F of Y. I've drawn out a coordinate system up here where I'm calling positive Y up and positive X to the right. From this here, this will have a positive Fx component and a positive Fy component for our support force here on the shaft of the idler. The top here we have our F sub R and F sub T. F sub T is equal to 100 pounds. F sub R we solved for is 36.4 pounds. And again over here, where our idler makes contact with our machine gear, we have, again, our F sub R of 36.4 and our F sub T of 100 pounds. And again, we note the direction of these based upon the rotation of that first motor. So we see here now this is going to be in the negative direction according to our coordinate system. This is the negative direction according to our coordinate system. And both of these are going to be in the negative directions based on our given coordinate system, where both of these components are going to be positive. So the next thing that we want to do is take the information from this free body diagram and do our summation of forces. So summation of forces in our x direction, I go through and look, well, I've got a negative 100 here, I have a negative 36.4 here, and I have a positive fx here. So summation of forces of the x is negative 100 pounds minus 36.4 pounds plus fx equals 0. Solve this for fx. Fx is equal to 136.4 pounds. Do the same thing in the y direction. I go back up to my free body diagram. I have a negative 36.4, a negative 100 here, a positive Fy there. So summation of force in the y direction is negative 36.4 minus 100 plus Fy equals 0. Solve for my Fy. Fy is 136.4 pounds. So if we want to get this guy here, it's simply a right triangle off of this. This squared plus this squared equals this squared. A squared plus b squared equals c squared. If we solve for c, c is equal to the square root of a squared plus b squared. Plug in our values. F is equal to the square root of f of x squared plus f of y squared. Plug in our known values for f of x and f of y. So f is equal to the square root of 136.4 squared plus 136.4 squared. Do out the math. So our force here for our support at the center shaft of our idler is 192.9 pounds. So for our next part of the solution, what we want to do is look at our radial bearing loads here. So what we can do is we come off our idler, take a look at that shaft that contained bearings A and B, and draw out our free body diagram. Now we know, based off of what we found before, that we have a load here on our idler shaft of 192.9 from our previous solution. What we need to find is what is this R sub B, the radial load at bearing B, and R sub A, the radial load at bearing A. Well, we know that bearing A is a distance of 1 inch away from our gear here for our idler, and B is 2 inches away from A, or 3 inches away from our load here on our idler. So what we can do now is, based off the information in this free body diagram, we can draw out a summation of moments. So summation of moments, we can do it about any point we want. I choose to do it about part B here. So summation of moments about B is equal to 0. So the reason I do that there is because we know this value here. If we do the summation of moments about here, there's 2 unknowns. Whereas if we do it about here, we only have 1 unknown there. So we can plug this in. Summation of moments about B. Well, what we have is we have our R sub A acting about B, which is R sub A times the perpendicular distance of 2 inches with our right-hand rule. That's positive. But then we have our 192.9 times 3 inches, that total distance perpendicular to this load here, which is going the opposite way, which is negative according to our right-hand rule. So summation of moments about B is RA times 2 minus 192.3 times 3 is equal to 0. Rearrange this, move it over, so we can see that RA times 2 is equal to 192.9 times 3. We can now rearrange and solve for R sub A, which is our only unknown in this problem statement. So R sub A is equal to 192.9 times 3 divided by 2. So our R sub A is now equal to 289 pounds. So that only gives us our R sub A. What we can do now is we can use the summation of forces in our y direction in order to solve for R sub B, which is our bearing radial load at bearing B. So we can say the summation of forces in our y direction is equal to 0. So what are our forces? Well, we have R sub B, R sub A, and our idler. So if we call our positive y going up, then we have a negative R sub B, a positive R sub A, and a negative 192.9 pounds there, all equal to 0. So then we do know that we've just solved for R sub A, so we can plug in our value of 289 for R sub A. This brings us to the summation of force in the y direction is equal to this negative R sub B plus 289 minus 192.9 equal to 0. Rearrange. Solve for R sub B. R sub B is equal to 289 minus 192.9. So therefore, R sub B is equal to 96.1 pounds, or our bearing radial load at bearing B is equal to 96.1 pounds. So now that we've gone through and solved for part A and calculated our radial bearing loads at A and B for the original direction of rotation of the motor, what if we were to reverse and do the opposite direction of the motor? So now our motor up here, as our dotted circle up here, is now rotating counterclockwise here. So if we come down here, we can then see that this reverses the direction of our F sub t here that we calculated. So now this is 100 pounds going in this direction, which is now our positive x. Our radial load F sub r here is still going down our negative y of 36.4 degrees here. And then over here we can see that now this load over here, F sub t, in between our idler and our machine gear here, is going up in the positive y direction as well. And our radial load is coming in here in a negative x direction like that. Where we have our support load over here, F, at the shaft of our idler, still has a positive Fy and a positive Fx. So now we can go down through and again do out for this free body diagram our summation of forces in the x and summation of forces in the y and see how it differs. So if we look at our summation of forces in the x direction here, we can see we have a positive 100 here, we have a negative 36.4 there, and we have a positive f sub x there. This is equal to 0. Plug in, rearrange. F sub x is equal to a negative 63.4. Then we come down here and we do the same thing here where we do the summation of forces in the y direction. In our y direction, what we have here is we have a negative 36.4 and a positive 100 and a positive Fy. So 100 minus 36.4 plus Fy is equal to 0, or our F sub y is equal to negative 63.4 pounds. So this gives us different values for F of x and F of y for our support. And we can see now this is in the negative direction, so we've assumed the opposite direction with our support pieces there. So that's one of the main differences there when we get to our F of x and our F of y. So now that we have new values for f of x and f of y for when the motor direction is reversed, we can go back to Pythagorean's theorem, a squared plus b squared is equal to c squared. So c squared is equal to square root of a squared plus b squared. Plug it in for our specific case here. F is equal to the square root of f of x squared plus f of y squared. Well, these are negative values now, so we have the square root of negative 63.6 squared and negative 63.6 squared there. Square those, the negatives go away. We end up with f equals to 90 pounds. So we do have a different value for our load F for our support on a shaft for our idler. Why? Well, reversing the direction of rotation, reverse the tangential forces, causing tangential and radial components to subtract rather than add when we did our summation of forces, which we just saw. Let's take a look at problem 15.5. In this problem here, we have a sphere. Let's take a look at problem 15.5. In this problem here, we have a spur gear reducer that has an 18-tooth pinion driven at 1500 RPM by an electric motor and a 36-tooth gear that drives a load involving a moderate shock. Now this is going to be important here that we're dealing with a moderate shock. A life of 106 pinion revolutions is required, and the transmitted load is given to us as Ft of 100 pounds. This figure includes a safety factor of 2. Conditions are such that we have a Km equal to 1.8 and a K sub T equal to 1. It is proposed that standard 20 degrees full depth gears will be used. So this is important here to notice this is 20 degrees. With both pinion and gear teeth being cut with low cost, average quality form cutting process. So all this information is going to help us as we're looking things up on figures, tables, and charts in the book to get all our properties. For steel, with a 235 BHN for the gear and a 260 BHN for the pinion. The diametral pitch is given to us as 10, and we have a face width equal to 1.0. They ask us to estimate the reliability with respect to the bending fatigue failure. So we're looking for reliability in the end. Now, if we look at our diagram down here, you see our pinion up top here, rotating at 1500 RPM. It has a hardness of 260 BHN. And our gear down here, here's the direction of rotation of the gear with a hardness of 235 BHN. And now we have our variables over here from the problem statement. Number of teeth of the pinion is 18. We have our pitch of 10. We have our B of 1.0 inches. We have our angle here of 20 degrees. We have our N sub G, our number of teeth in the gear of 36. Our K sub M was given to us as 1.8. Our K sub T was 1. Our F sub T was given to us as 100 pounds. And this is tooth cut with low cost, average quality cutting process. So this is all going to be important as we're looking up everything in the problem. Now what we want to find again is this reliability. So we can take all this information here, write out our givens, figure out what they want us to ask for, and come up with a bunch of different assumptions that we can use in order to simplify down our solution. So now that we've had a chance to look through the problem statement and the schematic diagram, the next thing we want to do is go through all of the information that they give us there, write down what variables we have, the values, how they relate to our problem, what they're looking us to solve for. So that's what we do here. Take a look. So we have a spur gear speed reducer, which is driven by an electric motor and drives a load involving a moderate shock. So that's the basic overview of the problem we have. Then we have all of the specific information here. So first variable we have here is our N sub P is equal to 18. And this is the number of teeth in the pinion. We have our N sub G equals 36, or the number of teeth of the gear. We have our P is equal to 10. We have our B, our face width, equal to 1 inch. We have our angle phi is equal to 20 degrees. We have our pinion hardness of 260 BHN, our gear hardness of 235 BHN, and we have our transmitted load F sub T is equal to 100 pounds. We have our temperature factor K sub T is equal to 1. We have our mounting factor K sub M equal to 1.8. We have our speed given to us, our motor speed is 1500 RPM. We know that it's moderate shock, and we know the required life is 10 to the 6 pinion revolutions. So over to the right here, we have our diagram. We have our big gear. We have our pinion. We know it's spinning at 1500 RPM. Here's the direction of rotation here. Here's the direction of rotation there. And they're asking us to determine an estimate of the reliability of the speed reducer with respect to bending fatigue failure. So we have a lot of information given to us in the problem statement. Now clearly have a spot to come back to, look at what variables they are, and how they relate to our problem. So now that we have all the information from the problem statement laid out in front of us, we understand what we're looking at as far as our variables, what they want us to solve for in the problem. The next thing we want to do is to come up with all the assumptions that we're going to make in order to solve this problem. So a lot of this information is given to us within the problem statement. The first thing that we want to do is make the assumption that the spur gears mesh at the pitch circles. Second, we assume that load sharing is not expected since the cutting process is of average quality. So this assumption comes from the fact they told us it was average quality. Third, we're going to assume that the effects corrected by the velocity factor kV correspond with the middle of the range in figure 15.24. So that's going to become important when we go to 15.24 to look this up. And then we're also going to assume that it's manufactured with form cutters. So this is important too when we're looking at the curves there to figure out which one we're choosing. Fourth, we want to assume that the pinion is driven by a uniform power motor while the gear drives a load involving a moderate shock. So this is given to us in the problem statement here. We're going to assume moderate shock. And the fifth assumption we're making is that the tooth fillet radius is approximately equal to our 0.35 over P. So to enable the use of figure 15.23 to estimate the geometry factor J. So now as we start our solution, the first thing we want to do is to take a look at this figure 15.23, and we want to do this with no load sharing. And for this figure, we know we have an N sub P, a number of teeth of our pinion is 18, and our angle here is equal to 20 degrees. So now we can go to 15.23 at the graph to solve for our J. So now we go to figure 15.23 in our textbook. This is a geometry factor J for standard spur gears based on a tooth fillet of radius 0.35 over P. So these are assumptions that we made, so we can use this graph here from figure 15.23. So what we want to do is take a look at the top, because we know we have an angle here of 20 degrees, not 25. So we're doing the top part A of this graph here. The bottom axis X is our number of teeth. Our y-axis over here is our geometry factor J. And this is, we have the load applied at the tip of tooth, which again, no sharing. So this is what we made the assumption of again as well. So we have this information here, so we know we're using this line in our graph. Our number of teeth, we know for our opinion the number of teeth is 18. We can go 18 here, go up to this line, come across over here to find our geometry factor. What we see from this graph here is that our geometry factor J is going to be 0.24. So for the next part of our solution, we want to take a look at equation 15.13. So we have here from 15.13, we have that V is equal to pi dn over 12. So this comes from our textbook. Now, what we want to know is what are each of these individual variables here? How can we reduce this in order to solve it with the information we're given in our problem statement? So we know that D is the pitch diameter in inches of the gear rotating at a speed of n RPM. So we have our speed and our diameter there. V is the velocity. So now we recall this relationship here that we've seen before. Our pitch is equal to n the number of teeth divided by D there. So we can rearrange this to solve for D. So if we do that here, D is equal to n over P. We're getting the number of teeth in our pitch here. So for our specific problem, this is the number of teeth in the pinion divided by our pitch there, where now we have all this given information here. So we can plug this relationship for D back into this equation 15.13 up here. What we end up with is that V is equal to pi d n over 12. Replace our D with n over P is pi n over 12p. So this number of teeth over our pitch here gets plugged into this equation here. So we end up with this relationship. And now we can plug in our known variables here. So we have pi, where n is n sub p of 18. We have our little n here, which is our speed, which is 1500 RPM. And we have our p here of 10, which is given in the problem statement there. So now we can plug this all into our calculator, solve for V. We find that our V is equal to 706.8 in units of feet per minute. Next, let's take a look at figure 15.24. So from assumption 3, we know we're dealing with form cutters here, and we have from the previous part of our solution that V is equal to 706.8 feet per minute. So let's use this information here and go to figure 15.24. So now let's take a look at this figure 15.24 in our text. This is for our velocity factor case of V. We can see down here in our graph that we have our x-axis, our pitch line velocity, our V in feet per minute. So we have that information given to us. On our y-axis, we have our velocity factor kV over here. And we have all these different curves here. And from our problem statement, we know that we're dealing with form cutters. So we're dealing with this graph E here. So we take this information that we have given. We've already solved for our V. So we know our V is 706.8. So we come down here on our axis, our x-axis here, we go over to 706.8. We go up until we intersect our curve here for form cutters. Then we come right across and we find that we're right at 2 for our value for our case of V. So now that we were able to get our velocity factor case of V from this figure 15.24 to be kV is equal to 2, the next thing we want to do is go to table 15.1. So this is for a uniform moderate shock. We need to look at table 15.1 to get our KO value. So now we'll head over to 15.1 and see if we can find that value. So we go to our textbook now and take a look at table 15.1. This is the overload correction factor, our K sub O, that we're looking for here. Now we can see along the side we have our source of power, and along the top we have our driven machinery here. So we know that it's a uniform source of power here, and we have moderate shock. So we come across here and we find that our value for our KO, or our overload correction factor, is going to be 1.25. So now let's go to equation 15.17, and we're going to apply this to the pinion. We look at this equation here, and we have that sigma is equal to our F sub t times P over B times J times our K sub V times K sub O times K sub M, where our J is going to be our spur gear geometry that we've already solved for. K sub V is the velocity factor. K sub O is the overload factor, and K sub M is the mounting factor. So of these variables for equation 15.17, the next thing we want to ask ourselves is, what do we have and where are the values? So we have down here, we have our J that we've already solved for, which is 0.24 for our spur geometry. We have our B, which is our face width, which is given to us as 1 inch. P is our pitch, which is given to us as 10. F sub T is 100 pounds, which is the transmitted load. Our K sub V is 2.0, which we found, which is our velocity factor. Our K sub O we found as well as our overload factor, and our K sub M is given to us now as our mounting factor. So we have a 1.8 for our K sub M. So all of this information here can go back up to this equation 15.17 and plug in. So we do that there, and we find that our sigma is equal to 100 times 10 divided by 1 times 0.24 times 2 times 1.25 times 1.8. When we plug in all of our known values here, we end up with our sigma is equal to 18,750 psi, or if we switch to KSI, it's 18.75 KSI. So if we continue on with our solution, looking for the rest of the variables, we see that we have CL is equal to 1.0 for bending loads. And for our gradient factor C sub G, we can go to the notes below equation 15.18 in our textbook. And we know that we have a P is equal to 10. This is greater than a value of 5. So if P is greater than 5, we see that our C sub G, our gradient factor, is equal to 1.0 as well. And then the next step in our solution is to go ahead to figure 8.13 back in chapter 8 of our textbook, with our value of SU is equal to 130 KSI in order to solve for our C sub S value. So that's what we'll do now, is we'll head back to figure 8.13 in our text. So now we head to figure 8.13 in our textbook back in chapter 8. This is a reduction in endurance limit owing to surface finish for steel parts. That is surface factor versus tensile strength for various surface conditions, where we have our tensile strength that we solved for our S sub U previously in the problem. So we have our S sub U and KSI of 130 KSI. Come down on our x-axis here. Follow this up until we hit the fact this is a machined part. So we go up to machined here. Hit this curve here, come across to our y-axis where we see our surface factor C sub S. We find that our C sub S is equal to 0.72. So now that we've had a chance to go to figure 8.13, we do find that our C sub S for a value of 130 KSI is equal to 0.72. So lastly, we need to solve for now our mean stress factor here. So now we can go to section 15.7 of our textbook, equation 15.18, and we find that for input and output gears, one-way bearings, for our specific case, we have a KMS is equal to 1.4 if we reference that section there. So now we can take all that information for these individual variables here that we found and go back to equation 5.18. We have now S sub n again is equal to S sub n prime times CL, CG, CS, K sub R, K sub T, K sub MS. With all what I've written down here is everything that we just solved for that we can plug back in. So we found that our endurance limit, or S sub n prime, is equal to 65 KSI. We have our load factor C sub L is equal to 1.0. We have our gradient factor C sub G is equal to 1.0. We have our surface factor C sub S is equal to 0.72. Our K sub R is what we're going to be solving for, our reliability factor. Our K sub T is given to us, our temperature factor of 1. And our K sub MS we just found as our mean stress factor as 1.4. So all of this information here for these variables we can plug back up into equation 5.18, and that's what we do right here. So now we have our S sub n is equal to 65 times 1 times 1 times 0.72 times our Kr, which we're solving for, times 1 times 1.4 is equal to 65.52 K sub R. Now for our case here, our S sub n is equal to our sigma that we solved for earlier, which is equal to 18.75. So we can plug this value in for our S sub n. So 18.75 is equal to 65.52 Kr. Then we solve for our Kr value here. We find that Kr is equal to 0.29. So up to this point here, we've really just been looking at the pinion. So now let's go back and take a look at the gear. So we're going to repeat that same process that we just did for all the information now, but for the information provided to us for the gear rather than the pinion. So the main differences here is that the gear has a number of teeth of 36, so N sub G is equal to 36. With that information, we can go back to that same figure, 15.23, look back for our J value, and we found that our J is now 0.27 as compared to before for the pinion it was 0.24. The other difference that we're going to do for the gear versus the pinion is solve for our SU here. So recall our BHN is going to be different. So now our BHN for the gear is 235. So we say our SU is equal to KB times our BHN, where KB is approximately 500 for steel here. So SU is equal to 500 times 235, or SU is equal to 117,500 PSI, or 117.5 KSI. Then recall our S sub n prime is SU over 2. So this is equal to 117.5 over 2. Or an SN prime value of 58.75 KSI. We go back through, solve for all those variables that we still need for equation 15.18. C sub L is equal to 1, C sub G is still equal to 1. Our C sub S is equal to 0.75, so that's again going back to that figure 8.13 from chapter 8. If we go back to that figure there, we can back out our C sub S value here, and we still have the same K sub MS value here of 1.4. So we can take all that information and plug back in to our equation 15.18. So that's what we do here now, is we plug back into equation 15.18. So if you recall again, 15.18 has all the same variables here that we just saw. We plug this in, S sub n is equal to 58.75 for our SN prime, 1 for our CL, 1 for our C sub G, 0.75 for our C sub S. K sub R we're still solving for, K sub T is equal to 1, and our K sub MS is equal to 1.4. We plug this in now here. S sub n is equal to 61.6875. We do out the math times KR. Again, our SN is our sigma here of 18.75 that we solved for earlier. Rearrange, solve for our KR. Our KR is now equal to 0.30. So now we have a KR for our pinion and KR for our gear, which are very similar, 0.29 and 0.3. So now what we can do is go to table 15.3. We'll plug in these Kr values here for the pinion and the gear in order to get our reliability. And we'll go there in a second. We find that our reliability is 99.999%. So referencing back to table 5.3 in our textbook, our reliability correction factor K sub R. Again, this comes from figure 6.19, so you can go back chapter 6 and reference that if you want, for an assumed standard deviation of 8%. So we look at our K sub R values. Again, we had a 0.29 and a 0.3, so we're maxed out way over here to the right. So we're a reliability factor of 99.999%.